Thank you for joining us for today's webinar. Today's webinar, entitled Measuring and Assessing Constructs, Exploratory Factor Analysis, Confirmatory Factor Analysis, and Average Variance Extracted, is being sponsored by the Society for the Psychological Study of Social Issues, also known as SPSSI, and has been organized by SPSSI's Graduate Student Committee, which runs both a policy-focused webinar series and a methodology-focused webinar series. I'm Cindy Lucas, SPSSI's Communications Director. I will now turn the webinar over to Angela Robinson, who's also a member of SPSSI's Graduate Student Committee. Angela will be serving as today's webinar facilitator. Thanks everyone for joining us, and I hope you enjoy the material.
Great, thanks so much, Cindy. As Cindy mentioned, I'm Angela, and I just wanted to give some quick info about SPSSI membership. Cindy, you can advance to the next slide, please. So SPSSI was founded in 1936 and has grown to a group of over 3,000 scientists and researchers who share a common interest in research on the psychological aspects of important social and policy issues. As an organization, we aim to bring theory and practice into focus on human problems of the group, the community, and nations, as well as issues that have no national boundaries. SPSSI is an independent society and is also Division 9 of the APA and an organizational affiliate of APS. SPSSI welcomes the membership of anyone interested in joining the society, and you can visit spssi.org for more information or to become a member. Next slide, please. As an organization, SPSSI offers its members a wide variety of opportunities. In addition to offering an intellectual home, networking opportunities, conference collaborations, awards, and fellowships, we also have a peer mentoring program, a policy and methodology webinar series, writing opportunities in our graduate student newsletter, and more. These projects aim to support graduate students and faculty in their scholarly and policy-related pursuits. If you'd like to learn more, please check out our social media outlets for more information about SPSSI and opportunities that we offer to our members. Next slide, please. And with that, I will introduce today's speaker, who is Joshua Wright, a third-year PhD student in social psychology at the University of Western Ontario. He's also a member of the collaborative program in migration and ethnic relations, and he has broad interests in religion, culture, and intergroup relations. He studied the effects of various religious practices on the extent to which people justify violence against others, competition and intergroup bias, psychological perspectives on terrorism, and the nuances of Confederate battle flag support in the American South. Most recently, he's working on a model of intergroup relations in the American South based upon the construct of psychological ownership. He's a recipient of the Bain Sukumuni Award for Early Career Research from the International Council of Psychologists. So with that, I'd like to give a warm welcome to Joshua on behalf of SPSSI and the Graduate Student Committee. Thanks so much for joining us today to share your knowledge, and I'll turn it over to you.
Thank you very much for that warm welcome, and thank you everybody for joining us on here. Today, we're going to do a number of things. We're going to talk about exploratory factor analysis and how we can evaluate our measurements. We're going to talk about confirmatory factor analysis, and then I'm going to introduce you to something that doesn't really get used much in psychology. It comes a bit from the business literature, but a concept called average variance extracted, which is a method that we can use to demonstrate discriminant validity. So if you go to the next slide. Next slide, please. Thanks. So the goals here is that one thing I hope you get throughout all of this is the importance of demonstrating the psychometric properties of our measurements. We find a lot of times in papers people use measures that have been used elsewhere, but maybe have never really been evaluated for dimensionality or other psychometric properties, and that can cause some serious problems for hypothesis testing later. I'm going to go into the purpose of EFA and CFA, how they're similar and how they're different, and then again, show you a method of demonstrating discriminant validity. My main goal is for this to be more or less a how-to guide, so that by the end of this, if you've never even heard of EFA or CFA before, you would be able to carry both of these analyses out at the end of this. And then we'll talk a bit about what are the main things that would need to be reported in a paper. As well as throughout, I will point out briefly just a few common myths that have to do with factor analysis and other similar topics as we go through. Next slide. So the purpose of EFA, what it's doing is that it is evaluating the underlying structure of the associations of some set of scores. So this set of scores, you can imagine this is just a big correlation matrix. And in the example here, I've used 6 variables or 6 items. So you can imagine that in some measure, each of these items, or each of these boxes here is one item in that measure. And what you're trying to do is understand what are the interrelationships between all 6 of these items. And so if you look at this example, there's kind of, in a visual way, you can probably easily see 2 things in this matrix. One is at the top left-hand corner, you have 3 very high correlations that are showing you the correlation between items 1, 2, and 3. And then you'll also notice in the bottom right-hand corner that you have another set of correlations that are also quite high. And those are the correlations between items 4, 5, and 6. And then the third thing you'll notice is that the other 9 boxes, that is all of the correlations between the first half, that is 1, 2, and 3, with the second half, 4, 5, and 6, are all quite low, and some of them are 0. And so visually you can tell right off the bat that items 1, 2, and 3 here all seem to kind of congregate together. They have something in common with each other. And items 4, 5, and 6 also have something in common. And so when we're conducting exploratory factor analysis, all we're doing is exactly this, except that we're doing it in a statistical method, because usually we're dealing with matrices that are so large that you wouldn't be able to fit them on a single screen like this to look at. And it also becomes a bit more difficult visually when suddenly you have correlations, that may be only slightly larger than other ones, rather than the big disparity we see here. If you go to the next slide, we have 2 primary things that we would want to accomplish with exploratory factor analysis. The first one is construct identification. And a good example of this is the big 5 personality traits. So when the big 5 were identified, it didn't start off by somebody deciding that, there was a theoretical rationale for having, 5 key personality constructs, and then they started, demonstrating this in studies. It started off actually by researchers going to dictionaries, compiling lists of hundreds of trait-like variables, and then having people fill out Likert scales on each of these variables. And via conducting EFA, they were able to determine that there really seemed to be only 5 key constructs that were explaining most of the variation across hundreds of trait-like variables. And so in this case, it's not necessarily about developing a measure, it's about identifying theoretical constructs that we don't yet know exist. The second reason we would want to do exploratory factor analysis is that we're actually trying to develop a measurement instrument. So in this case, we may already know what types of latent variables or constructs we should be expecting, and now we're trying to figure out a way to measure them. And so we sort of look at 2 things when we're trying to develop a measurement instrument. The first is scale dimensionality. And so EFA gives us information about how many dimensions, that is, how many latent constructs do we have in any given measure. And so this kind of brings me to myth number 1, which is that many people think that internal consistency reliability that we usually report via convex alpha tells you something about your measure or your variable being unidimensional, and it does not. You can in fact have very high internal consistency reliability that is a high convex alpha while still having a multidimensional structure. And so one of the problems with measurement in many papers is that we don't really know whether the measures or the variables being used in models are unidimensional or multidimensional, because people aren't reporting that information. The second thing that we get in this process of developing measurement instruments is that we get provided psychometric properties of the item. So we can determine whether an item really effectively captures the theoretical variable that we want it to capture. And we can also see whether an item is a pure measure of a construct or whether it's a measure that we can use to evaluate multiple constructs at the same time. Usually, when we're doing this, we're often doing these two things in tandem, so it's not necessarily that we're doing, one or the other. If you go to the next slide, what EFA is doing is it's determining the number of distinct constructs needed to account for the pattern of correlations in our matrix, with the assumption that it is our latent constructs that are exerting the linear influence on the measured variables. Okay, so it's not the measured variables that are causing the constructs, it's the latent construct that is causing these measured variables. And if you go to the next slide, the EFA and CFA as well, so what I'm talking about here applies to both exploratory and confirmatory analyses, but these are based on what's known as the common factor model. And what the common factor model says is that each observed variable is a linear function of one or more common, that is, latent factors, and then some aspect that's a unique factor. Okay, so the common variance in the common factor model is this amount of variance that's accounted for by the common factor that we've identified. And then this aspect of unique variance is a combination of two things. It's a combination of variance that's specific to the individual indicator, that is the individual item that we've measured, and then some element of random error variance. And we don't know where that random error variance comes from. It could be coming from a correlation with another item, or it could be coming from another construct that we haven't identified in our particular measurement. And so this brings me to myth number 2, which is that many people, even when they're conducting EFA in a paper, will actually conduct a principal components analysis. I just read a paper published in 2017 that was using PCA while arguing that they were doing EFA. The reason PCA is not the same thing as exploratory factor analysis is they're based on completely different models. So while EFA and CFA are both based on this common factor model, PCA is not. A few other things that principal components analysis is actually just designed to reduce scores on a battery of measured variables into a smaller subset of scores so that something is easier to measure with less items. But the goal, in fact, is to account for variances of the measured variables, not to explain the correlations between those measured variables. The second thing is that principal components, which is the outcome that you get from a principal components analysis, these don't necessarily correspond to meaningful latent variables. That is, what you get out of PCA may not be theoretically viable components. And finally, I'll just note that it is true that in some cases, both principal components and exploratory factor analysis will give you similar results. This is dependent upon what I'll show you in a minute is the communality, the amount of variance that all your different items share with each other. So in cases where you have a lot of shared variance between items, you may in fact get similar solutions for both PCA and EFA. But in cases where you have lower communalities or less shared variance, PCA will give you an admissible solution. Let's go to the next slide. This is just a graphical depiction of the common factor model with a few values put on here. So what you can see is that on the left-hand side, you have two identified common factors. And so that is that all of the square boxes, which are the item level variables on the right, are all being explained by the two common factors on the left. And in EFA, we don't specify where individual items have to load. So we actually, through both the black lines and these blue lines that I've added in, we allow the items to load on one or both or more factors if we had a higher multi-factor structure. And so you'll have this factor loading that tells us the strength of that relationship between the common factor and the indicator. And then off to the right, you'll see that you'll have some element of that random error causing the indicator as well. If you go to the next slide, this is just to show you another example of the visual method and how it gets a bit tricky. So the data that's in this correlation matrix here is the same data that the previous slide, that model, was based upon. And so as you can see, in this case, you have, in the bottom right-hand corner, you have some moderate correlations there tying, items 4, 5, and 6 together. And then in the middle in red, you still have, even though these are lower correlations, there's one there that's, 0.219. So it's a little bit more difficult to tell in the visual method here whether we really have two distinct common factors or whether we may just have one big common factor and some of the correlations with some items are just a little bit higher than others. If you go to the next slide, so when you run exploratory factor analysis, there's two primary outputs that you're going to want to look at. The first is the factor loading. And the factor loading is an estimate of both the strength and the direction of influence that the common factor has on a measured variable. In the case of ESA, these are going to be standardized. And so what you're really looking at is that for a 1 unit change in the common factor, you'll have X amount of change in the measured variable itself. The second thing that you'll want to take a look at is the communalities. The communalities provide us a measure of the amount of variance in an individual item that is accounted for by the common factors, by all the common factors combined. So it's actually a sum of the squared factor loadings for that particular item level variable. Go to the next slide. There's a number of decisions that we have to make prior to getting into this example that I'll show you. The first is you have to be quite clear about your domain of inquiry, whether because you're measuring, attempting to measure a particular construct or because you're trying to identify some kind of theoretical construct. So you're generally going to be fairly narrow in the domain of inquiry. Recommended number of items is that depending on your expectation for the number of common factors, you need to have a minimum of 3 measured variables per common factor. So, if you're doing this, let's say you've taken a 5-item measure, and you're hoping that, you're going to demonstrate that there's 2 underlying sub-factors, you're likely not going to identify that with that number of items. The next thing to consider before even really collecting data is that you're going to have to make determinations on sample size. And there's really no one-fits-all answer to how big your sample needs to be in order to conduct an ESA, because it depends upon the communalities. So that means that how many people we need in our sample is dependent upon the shared variance between all of the item level measures. So in the cases where we have really high communalities, like around 0.7, we can get away with small samples, about 100 people, and in some cases even less. But in the case where we have really poor communalities, this might be around 0.40, you're going to need hundreds of people. And so it's generally, at least to be somewhat conservative, is that I would never have an expectation that I would have anything more than, let's say, moderate communalities that might be around like 0.55. The final thing is you have to make some determination on missing data. In the case of doing EFA in SPSS, you'll have a number of different options: list-wise deletion, pairwise deletion, replacing for the mean. If you select one particular way of doing EFA, that is one extraction method called maximum likelihood, this basically works as its own imputation procedure, and then you don't have to worry necessarily about the missing data at all. If you go to the next slide. So once we have our data and we're running the analysis, there's a couple things that you have to make decisions on. The first is that you're going to have to choose a fitting method. So there are two primary fitting methods that I'll show you in a moment that you'll have to select between. The second is you're going to have to decide whether you are theoretically expecting a specific number of common factors or whether you're willing to just let the data and the statistics tell you how many factors there are. And I'll show you in a minute why I think that's a bad idea. And then finally, you're going to need to choose a rotation method. And so just preliminarily, I'll tell you that in my examples, what I'm using is a scale from Kosterman and Feshbach, who are interested in breaking down measures of national identity into two components, primarily patriotism and nationalism. And this is important because nationalism and patriotism have both been found as different expressions of national identity to affect outgroup attitudes and attitudes towards immigrants in distinct ways. And so as we go through an example, I'm going to use a 20-item measure of nationalism and patriotism as the example for the ESA and the CSA. If you go to the next slide, I'll talk about the choosing, the methods of fit, or the extraction method. So the two primary ones that we have are principal axis factoring, and then we have maximum likelihood. Principal axis factoring is actually the older of the two, and probably still the most commonly done. And a little bit newer is maximum likelihood, and they both have kind of benefits and costs. So the greatest benefit of principal axis factoring is that there's no distributional assumptions here. So it doesn't matter how skewed or kurtotic your data is. Principal axis factoring also tends to be less prone to improper solutions, and it's better able to extract weak factors. So in some cases where theoretical constructs are very difficult to measure, you can probably expect that you would have some weak common factors. And PAF is also better when you have a fewer number of indicators. So if you're kind of verging on that minimum number of 3 to 5 indicators per common factor, then principal axis factoring may be a better choice. The greatest benefit of a maximum likelihood, in contrast, is that you get model fit statistics. So most people think about model fit as being something that only applies to confirmatory factor analysis, but it actually also applies to EFA. In the case where we use maximum likelihood, we can get the same model fit indices that we get in CFA models. Maximum likelihood comes with the cost that we have to assume multivariate normality. And so what this means is that each measured variable, that is each of our items, is assumed to have a normal distribution. And it's also the case that we assume that all the associations between any pairs of those items are linear relationships. So if you're unsure about these, then PAF is going to be a better option. Maximum likelihood is still fairly robust to non-normality. It's not usually the case that it's problematic until skewness gets above about 2.0 and that kurtosis gets above about 7. If you go to the next slide. So I have a number of slides like this throughout, which are really just kind of part of the how-to portion. So if you go home later and you're unsure of, let's say, where to click in SPSS, you can look at these slides, but I'm not really going to talk about them much. So if you go to the next one, this will be the next step as you're conducting it, and the next step. So our next step after choosing an extraction factor, let's just say in our case that we've opted to go for principal axis factoring because we think we probably have some fairly extreme non-normality. The next thing we have to do is determine a method to decide how many factors that we're actually going to identify. And there are a number of different ways to do this, and it is sometimes the case where each of these methods will give you a different number of common factors. And so I'll talk about each of these in turn. The first is called the Eigenvalue 1 rule. And if you go to the next slide, I have a bit more about this. So what an eigenvalue is that it's a metric of variance in a correlation matrix that's explained by a single common factor. And so larger eigenvalues represent more explained variance in the correlation matrix. So in the Eigenvalue 1 rule, what we're doing when we're looking at the output is we're identifying each eigenvalue that's greater than 1, and we're considering anything above greater than 1 to be a common factor in our model. The problem is it leads to somewhat arbitrary decisions where, let's say, something with an eigenvalue of 1.1 will be selected, but something with an eigenvalue of 0.95 will not. It's also the case that the Eigenvalue 1 rule generally leads to substantial overfactoring, and you can typically expect that for about every 4 or so items in a measure that you're probably going to get or identify a common factor for that. And so there are a couple better ways of doing this. So on the next slide, you have what's called the Chisquare test. And the Chisquare test does it takes the same eigenvalues that we're using in the eigenvalue 1 rule, except now what we're doing is we're looking for the last major drop. So anything that would consist of a really big drop between two eigenvalues, we then want to consider that eigenvalue to be a common factor. And I'll show you a graphic of this that will make it a little bit clearer. The Chisquare test is still a bit subjective in that deciding which ones are major drops or not can sometimes be difficult to do. And then in some cases, it's quite easy and it's quite clear. The final option is to do what's called parallel analysis. Go to the next slide, which is a comparison of the eigenvalues from our sample data to eigenvalues that we can generate from a random data set. And so I've linked in here an engine that you can put in basically your sample size, the number of items that you have, and you can generate a random data set with random eigenvalues. And then what you're doing is you're comparing the eigenvalues from our data to the random data with the assumption that we're considering it to be enough explained variance to be important if the eigenvalue from the real data, that is our data, is larger than an eigenvalue, that is an amount of variance from a random data set. Sometimes it can be a bit lenient and it can lead to overfactoring, but the good thing about it is it's very mechanical. So there's not really any subjective nature to using this as a method for determining. Let's go to the next slide. This is just another how-to slide. So it shows you what you can click to select your different methods, where to click if you want your scree plot, and so on. On the next slide, so I've talked now about first selecting a fitting method, either principal axis factoring or maximum likelihood. I've talked about the methods of selecting the number of common factors. And then the last thing we have to do is we have to identify a method of rotation. I'm not going to go into rotation in any really conceptual detail, but when the PDF of the slides go out, there are a number of slides that are hidden from view now that will be in that PDF that will explain some of the conceptual material in a bit more detail. But for rotation, we have two options. We have what's called an orthogonal rotation, where the rotation is required to maintain 90-degree angles. And then we have an oblique rotation, where we can change those angles to less than 90 degrees. In the case of orthogonal rotation, this assumes that we have uncorrelated common factors. Orthogonal rotation has tended to be the most common form of rotating because before we had really powerful computers, you had to do this by hand, and doing oblique rotation was almost impossible to do by hand. And so this has sort of just been a trend that's reminiscent of the days before powerful computers. And now it's generally recommended that you don't ever use orthogonal rotation at all. And so this brings me a bit to the third myth, which is that many people believe that if they force their model to use orthogonal rotation, that it in fact forces your common factors not to be correlated. This is not true. This is an assumption of orthogonal rotation. So if you know that common factors are likely to be correlated, then there's no benefit to you using orthogonal rotation. Oblique rotation simply selects the model with the best simple structure, regardless of whether it allows or doesn't allow correlated common factors. And so it makes no pre-specification on whether they can or can't be correlated. So in the case where common factors are correlated in your model, oblique rotations are going to provide you better simple structure, which is going to be better for interpreting the factor loadings of the model. In the case with oblique, if you really don't have correlated common factors, which would be extremely rare in social science research, then oblique rotation methods will provide you essentially the same output as will an orthogonal rotation. So in general, it's never beneficial to use orthogonal rotation. If you go to the next slide, this is where you'll find a number of the various options for doing rotation methods. There are a number on here. Promax is really, I think, the recommended method for oblique rotation. There are other ones like direct Obermann is also a oblique method of rotation that you could use. The rest of them are orthogonal rotations, so I wouldn't recommend using either of those. It's important to note that when you're rotating your model, doing the rotation only helps with interpreting the model. It's not actually changing the model. So it doesn't change the fit of the model. It doesn't change the amount of variance that's explained by each of the common factors, and it doesn't change your communalities. In the case of oblique factors, or oblique rotation, the factor loadings will be interpreted as regression coefficients. So that means that it's, it is that standardized relationship while partialing out the effects of the other common factors. So you would interpret it just like you would in a standard regression model. Go to the next slide. Here, just for those of you that like to use syntax in SPSS, I have syntax that you can copy and paste and adjust for your own uses here. On the next slide, for those of you that use M+, which is my preferred software, I have code here as well that you could just change out the code for the file, and you can name the variables whatever you want them to be named. You plug in the estimator that you want and the rotation method you want, and this will run your EFA for you. On the next slide, I'll talk a bit about what output you're going to see, and then we'll get into this example where I'll show you what it actually looks like on my screen. So the first thing you should look at is, again, the communalities, which in the case of the extracted communalities is going to be the variance in the items that's accounted for by all of the common factors. So generally, we want to have fairly high communalities, and so in EFA, what you're probably going to look for is any communalities that would be like below 0.5, and you would consider those for elimination, but I'd never recommend eliminating items simply based on the statistical properties. You'll want to go back and make sure that there's not some key theoretical reason why a particular measure would still need to be included. In the output, you're also going to find the information that will tell you the number of factors and the variance that each factor explains in the correlation matrix. And again, this will be in whatever method that you've selected. The first matrix that you'll see will be the factor matrix, which shows you the correlations between items and factors, not accounting for any correlation between the common factors. So this is essentially showing you the correlation before rotating the factor loadings. The pattern matrix, which is the one that you really want to pay attention to in oblique rotation, shows you, again, the regression weight for the effect of the common factors on each of the measured variables while controlling for all the other factors of the model. And then the next one is the structure matrix, and this is showing you the zero-order correlation between items and factors after rotation. And then the last one, which you'll only see in the case of oblique rotation, is that you'll see a correlation table for the correlations between each of the common factors. To go to the next slide. So this is what you're going to see, at least in SPSS, when you do the communalities. The output is basically the same in M+. And again, what you want to look at is the extracted communalities. These extracted communalities are the variance in items accounted for by the common factors, whereas the initial communalities are simply the squared multiple correlation based on all the other measured variables, okay? So here in this case, where we have our nationalism, patriotism subscales, and what we're trying to do is identify that there's a two-factor solution here, the first thing I would do is look at these extracted communalities, and you'll notice a couple things right off the bat. That some of the items, like the one that says, in general, I have very little respect for the Canadian people. This was done on a sample of Canadians, that this is a particularly low communality, which tells you that that item doesn't really have a lot in common with all the other items in the matrix. And so all of these, you would then want to go back and consider whether you really think that's a good item or not. On the next slide, you'll see the eigenvalues greater than one rule, as well as the total variance that's explained by each of the common factors. So in this, again, we had 20 items total here. There were 12 what we thought would be the patriotism items and 8 that we thought would be nationalism items. And if we were to use the eigenvalues greater than one rule, then we would identify 5 common factors here. that explain roughly 55 to 56% of the variance in the correlation matrix. And when we look at the factor loadings, I'll show you in perspective why this is not a good method. If we go to the next screen, you'll see that if we selected the scree plot method, that is where I'm plotting the same eigenvalues that you saw on the previous screen, except now what I'm doing is I'm looking for the last major drop. And so as you can see, we have a major drop between the first eigenvalue and the second, and then another fairly major drop between the second and the third. And then after that, it seems to level off. So in this case, I would interpret this to be a two-factor solution. If you go to the next slide, you'll see what output we would get if we use the parallel analysis method. So in this case, on the right-hand side, you can see the means and then the 95th percentile of the confidence intervals for the means of a random set of eigenvalues generated from a random data matrix. And then what you're doing is you're comparing the values for your factor 1 with the factor 1 from the random data set. And so you would identify, okay, my eigenvalue for my data is larger than what I would expect if this were random data, and so I would consider that to be the first common factor. In the second case, where you're comparing 2.3 to 1.46, I would again consider that to be the common factor in the model. And then when we get to number 3, the 1.31 versus 1.37, 1.38, you would look at that and see that in actuality, we are actually seeing more variance explained in the random data set than we are in our model. And so I would consider everything beyond 3 to not really be factors in the model. And so in this case, parallel analysis and the scree plot are both converging and telling us that we probably have a two-factor solution. If you go to the next screen, this is where you're going to get your factor loadings for the model. In this case, what you want to be looking for is each of the factors identified at the top, and you want to go through and you want to see that first, that the factor loadings for items that you expect to load onto that factor would be high. So, in the case of factor 1, you can see all these patriotism items at the top tend to load particularly highly. And then in other cases, you'll see that there's some fairly low loading. If you go to the next slide, I think I've actually penned some of these so you can see them better. So on the left-hand side, we have all the patriotism items, and on the right-hand side, we have all the nationalism items. So the first thing to look at is that factor 1, you can basically see that most of those patriotism items generally have a good factor loading. There's a few that are kind of low, right, that aren't loading on factor 1. For example, if you look at the item, it's not that important to serve my country, you'll see that that's actually loading on a third common factor based on the eigenvalues greater than 1 rule. And there are a couple other items loading on this third factor that I've identified by the blue arrows. And if you look closely at the wording of the items, you'll notice that 3 out of 4 of these are reverse scored items. And so what the eigenvalues greater than 1 rule is actually doing is identifying what we call a methods factor. That is, it's taking all the reverse scored items and considering to be their own common factor. And so this is where, understanding the theory of what you're trying to do is very important, because in this case, it's not actually extracting this factor based on the content of the items, it's extracting them based on the fact that they're reverse scored. And that's not something that we're interested in doing, for our conceptual model of national identity. The other error that you see with the patriotism scales, you actually see that you have a patriotism item that has a fairly high cross loading. So the one that says in general, I have very little respect for the Canadian people, it's actually loading more highly on a 5th factor than it is on what here we're considering to be the patriotism factor. And so something with large cross loadings is something that you're going to want to consider for deletion, because it's not strictly measuring the common factor or the construct that you're hoping that it will. A couple other things on here is on the right-hand side where we have all the nationalism items. If you look at the top blue arrow there, we actually have a nationalism item, or something we thought would be a nationalism item, that's actually loading onto the patriotism factor, that is factor 1. And so later, you would probably want to consider either removal of this item or transitioning this item onto the patriotism scale when you do the confirmatory factor analysis later. And the last thing is that we have this fourth common factor in the fourth column on the right. It's made up of simply 2 nationalism items. Because generally we need to have 3 to 5 indicators per common factor, you would want to consider either removing these items or repositioning them, onto reconsidering what factor you think they really apply to. In this case, you're getting, again, probably another methods factor where it's taking that last item, which is a reverse scored item, and placing it on this separate factor. So when I look at this, what I kind of see is I would probably move towards the 2-factor solution that we get from the scree plot and the parallel analysis. And so then when I go back into EFA, I would simply select that rather than using the Eigenvalue 1 rule, that I want to specify a 2-factor solution. And so if you go to the next slide, and then we'll skip this one for now, to get to the next one. These are kind of the questions that based on the information you just saw, that you kind of need to answer. In each of those factors, are they interpretable, especially on theoretical grounds? And we identified a number that don't really make sense based on the theory and really seem to be just methods factors. Is each of the factors well-defined? That is it composed of a number of strong indicators? If something has weak indicators, it doesn't have enough indicators, then the factor is not well-defined. Again, is the factor being driven by those methods effects? Does it have poor indicators? And then are there substantial cross-loading? So these are all some reasons that you would want to consider either the elimination of items or reconsidering what the item is actually measuring. If you go to the next slide, I think I just have this again so that you could look back to it and can kind of consider some of those questions. Yep, so let's go right there. So here, this is just a graphical depiction of once I've redone this exploratory factor analysis, specifying a 2-factor solution in comparison to the previous graphic, this one actually looks quite good. You have all of these items there on the right-hand side that are loading on that axis for factor 2, but not really loading much on the axis for factor 1. And then you have all of those items there that are in the center, kind of towards the top, that are loading positively on factor 1 and kind of in the midpoint on factor 2, which is what you want to see in your rotation if you're meeting the assumptions of a good simple structure. So if you go to the next slide, so everything that I just showed you, right, are the individual steps and the thought process that you need to go through while conducting an EFA. Talking about CFA is going to be quite a bit shorter because it's based on the same factor model. So it's not the case that a whole lot changes. In confirmatory factor analysis, what we're primarily wanting to do is simply confirm the structure that we think that we've identified in an EFA. And you're going to tend to want to do these on different samples. So we would have one sample where we've conducted our exploratory factor analysis. In our case, let's say that we've identified a 2-factor solution. And now in a separate sample, we want to see if we can confirm that 2-factor solution really exists. Because again, what we're trying to say is that this model exists in the population, not just in that single sample. The main difference between CFA and EFA is that in CFA, we have to pre-specify all the aspects of our model. Whereas in EFA, we simply allow various cross-loadings, we allow all the items to be correlated, and so on. In confirmatory factor analysis, if we wanted all these item correlations or if we wanted cross-loadings, we would need to specify them. If you go to the next slide, so what things do have to be specified? Well, first we have to specify the number of factors. So in our case, again, I would want to specify a 2-factor solution and see what the model fit of a 2-factor solution identifying a patriotism factor and a nationalism factor is. The second is that we have to specify these patterns of the indicator factor loadings. So if I think that all of what I think are patriotism items load only on the patriotism factor, then I specify those only on the patriotism factor. So I'm not going to allow them in the CFA to load onto the nationalism factor, which we did in the ESA. And then finally, if I think it's the case where I have items that have correlated error variance, then I can specify that those that the random error variance between two items correlates. And the reason that you might want to do this is if you thought that there's some other common factor that you haven't included in your model that actually causes some of the variance in multiple items, then you can account for that by specifying that the random error variance would be correlated. If you go to the next slide, we can, so this is just syntax you can use for conducting a CFA. And then the slide here is just showing you the model of the CFA once I run the syntax on the previous slide. So again, it looks just like our example of the common factor model. You have your two common factors that we've specified. We specified the loadings on each of their indicators, the 12 patriotism items, the 8 nationalism items. You have your standardized factor loadings in the middle. So this is for a basically 1 point increase in patriotism, you would see a 0.664 increase in the first item there identified as KF1. And then we can see the correlation between those factors, which in this case you can see are quite high. And compared to the sample I used for the EFA, that correlation is quite a bit higher. I think that the correlation within the EFA between the common factors was only about 0.32. And again, off to the right, you have that amount of random measurement variance on each of those indicators. So again, here, we're sort of looking for the same thing. We're looking for items that aren't loading particularly well, and generally, through the EFA, we would have identified those. So if you see the very bottom one, that's KF20 loading at 0.283 on the nationalism factor, that's quite low. And so to keep that in there, I would have to have a theoretical rationale why that item is really important. Otherwise, when we transition from the EFA to the CFA, we probably would have removed that item. If you go to the next slide, I'll show you what the output looks like here when you're running the CFA in Plus. You get a number of fit indices that you can look at. You get a test of the model fit using the chi-square. You can see how many free parameters, how many degrees of freedom are in your model, and so on. And on the next screen, I'll talk about assessing model fit. So there are 3 general domains that we use for assessing model fit. The first is that we have absolute fit measures. Then we have absolute fit measures that adjust for model parsimony, so they take a penalty, the more free parameters that we're trying to identify. And then we have comparative fit measures that measure the model we're testing compared to some other pre-specified model. On the next slide, the chi-square test is what's known as a test of exact fit, and you'll see all of these measures of fit on that N+ output that I showed you earlier. What it does is it tests whether the model that I've specified in my confirmatory factor analysis has perfect fit. That is, does it perfectly reproduce the covariance matrix? And because it's a test of exact fit or perfect fit, it almost always fails in large sample sizes. So it would only be the case in small sample sizes where you would perhaps want to place emphasis on the chi-square test. On the next slide, this one is an absolute fit measure, the square root measure of approximation. And here what it's doing is it's measuring the absolute difference between the input correlation matrix that we're using to calculate our parameter estimate and the predicted correlation matrix based on our parameter estimate. And the discrepancy between those two is this value. So the SRMR is going to be values between 0 and 1, where lower values show better fit. That is, a lower value shows less discrepancy between the input correlation matrix and the predicted correlation matrix. We'll generally consider acceptable fit to be values less than about 0.08 and good fit to be less than about 0.06. One of the problems with the SRMR is it performs poorly with categorical indicators. So if you're not using continuously measured variables, then you would want to exclude this indices. On the next slide, here we have the root mean square error of approximation, which is a form of an absolute fit index, except that now it's adjusted for parsimony. So the RMSEA takes a penalty for increased freely estimated parameters. It measures the extent to which a model fits reasonably well. So in contrast to the chi-square fit test, here we're only comparing to reasonable fit. One of the big benefits of RMSEA is that you get confidence intervals in the output, regardless of what platform you're using. And this means we can kind of test whether we pass what we might call a good fit test versus a bad fit test. One of the problems with RMSEA is it tends to falsely reject models with small n. So contrast to the SRMR, this one is quite a bit better in larger sample sizes. We consider acceptable fit to be values less than 0.08, and good fit to be less than 0.06. And again, because you get a confidence interval, you can look at whether that confidence interval goes over 0.08 and whether that confidence interval goes under 0.05 or 0.06. And so in a case where your confidence interval goes over 0.08, then we can't really be sure that we have acceptable fit. And in the case where we maintain our confidence interval under 0.08, but that it also goes below 0.06, then we actually have some chance that rather than just good fit, or rather than just acceptable fit, we would have good fit. On the next slide, I'll show you the two comparative fit indexes, the CFI and the TLI. So what these do is instead of measuring the absolute fit of the model, these compare the model that we've specified in our confirmatory factor analysis to another pre-specified model, typically the null or what's called an independence model. And the null or independence model is one that's specified where the covariances among all the input indicators, that is all the input items, are fixed to 0. That is, we assume no correlations between any of those items that we've entered into our CFA. So the values range from 0 to 1, where higher values indicate better fit. Acceptable fit for both of these tends to be around values of 0.9, and good fit would be closer to 0.95. The difference between the CFI and the TLI is that the TLI takes a penalty for model complexity in the same way that the RMSEA does. So the more freely estimated parameters, the more of a penalty that the TLI takes. So it will generally be the case that you'll get smaller TLI values than you get CFI values. And TLI has the problem that it tends to falsely reject models with small n, similar to the RMSEA. If you go to the next slide, so before I go into average variance extracted, I'll just note that because we have kind of these three different types of fit indices, it's generally the case that you want to pick one from each of those areas. So you want to at least have an absolute fit index and then also a comparative fit index. You don't have to report, for example, both the CFI and the TLI. You would simply select one of them because they're essentially telling you the same thing. And then in the absolute fit indices, you would want to select at least one of those as well. So either the SRMR or the RMSEA are generally the best choices. So when I report these things in papers, I tend to report the RMSEA with its confidence intervals, and then I report the TLI because I like the correction for the model parsimony. So the last thing that I'm going to briefly discuss, if you go back one slide, is what's called average variance extracted. The value AVE represents the amount of variance that's explained via a construct, right? So one of our latent variables, compared to the amount of error variance within that measure. So you can imagine that generally, if we have an AVE value of 0.50, that would indicate that we have just as much error variance, that is just as much unknown about our common factor as we have variance explained, or variance that we know about. So we can use this as a method of examining discriminant validity, both between common factors in our model, so in this case between patriotism and nationalism, but also between each of these common factors and any other measures or variables that we include in a broader structural equation model. So the way that we assess discriminant validity with this is that we compare the amount of variance explained via our latent variable, the amount of shared variance between the two constructs. And what we want to see is that we explain more variance in our latent variable than it has shared variance with another construct. So if you go to the next slide, you can see here the steps in doing this, because all of this is done out of the CFA model. And if you go to the next slide, I will show you how this is actually done. So in the case of our CFA, which we've already seen, I would take all the factor loadings for, in this case, my two factors, patriotism and nationalism. I would take each of those loadings and square it. Then I would take the sum of the squared loadings for each of my common factors. So we have the 3.79 for the 12 patriotism items, and then the sum of the squared loadings here, with the 1.99 for the nationalism item. And then what I do is I simply divide that sum of squared loadings by the number of items in the common factor. And then I get the amount of the average variance that's extracted from each of those items by the common factor. If I take the square root of it, I get the values that are on the right. This is what we call the square root of ADE. And this is the measure that we want to compare then to the correlations both between our common factors and also between any other measures within our overall structural equation model. So if you go to the next slide here, I've just shown you this all put together in a single table here. You can check out this paper if you want to look at CFA more generally, a good example of this. So what I've done here is I've taken all the variables in a model that are all on the left and across the top, and I've taken a correlation matrix. And then on the diagonal for each of my variables, I've placed that square root of the average variance extracted value. And so then you can easily look at those bold values, the squared ABE, and simply compare it to everything underneath it to those correlations, right? And what you're looking for is that those bold squared ABE values would generally be higher than the correlation of that particular variable with any other variable in the model. And so in this case, you can see that we generally show discriminant validity in this case between all of these latent constructs on the left-hand side with every other latent construct in the model. And finally, I have some slides here that I won't go over, but these are just various resources, some very good books on EFA, CFA, and structural equation modeling if you want to take this a bit further. On the next slide, various of the key articles regarding fit indices, the various cutoff criteria, and so on, as well as the Fresnel and Larker article where you can find the AVE material. And then finally, David Kinney's website. He has a number of very good webinars and a lot of good information freely available there. So at this point, if we have time for questions, feel free, and I will answer them to the best of my ability. Otherwise, my email address is on the last slide there, and feel free to email me later if you have questions about any of this material.
Great.
Thank you very much.
Thanks so much. Thanks, Joshua. So we've had some questions coming in the Q&A, and we're almost out of time, so I'll just give you a couple, and then if people want to email you with others, that would be a good way to follow up. But we had a couple questions about communality that I thought might benefit from a live answer. So one question, I'll just combine a couple of questions from Lucas and Achu. So we had questions about how you can estimate the communality before gathering data, if there are any strategies for that, and then what you can do in cases of low communality.
Sure. So estimating them, there's not really a surefire way to do this. It's going to be primarily based on your understanding of the theoretical constructs themselves. Presumably, if you're developing a measurement instrument, you've written all the items, and so by using kind of basic keys of item development, which would be kind of in a basic psychometric course, you could sort of ensure that your communalities would likely be at least moderate. In the case where you don't have high communalities, these would be items that you would want to consider for deletion. So that's why it's really important to oversample items. And so, if in the case where I'm trying to develop a 6-item scale, I'd be much better off having a 12-item scale to start with, and then eliminating those items that have really low communality.
Great, thank you. And we'll just do one last question. Sorry if we weren't able to get to your question today, but this question was from Marvin, and it's about how to interpret fit indices that look perfect, so like a CFI of 1.0, an RMSEA of 0.000, for example.
Usually if you have something like a TLI or CFI that's showing 1.0, then you probably you may have a just identified model, which means you don't have any freely available parameters to estimate, and so the fit of your model is actually perfect because you're not estimating any parameters. Otherwise, like I would automatically start looking at my factor loadings and see what's going on with those, because chances are if you have a value that's either that high or that low in the case of RMSEA, it's probably the case that there's something wonky going on or misspecified.
Great. Okay, thanks so much. So again, if we didn't get to your question, I'm sorry that we weren't able to, but please feel free to get in touch via email. And I just want to conclude today's webinar by giving a big thank you to Joshua Wright for this informative and engaging presentation. And I'd also like to give special thanks to Cindy Lucas, SPSSI's Communications Director, and Sarah Mancall, who's our Policy Director, who were instrumental in coordinating and promoting this webinar today. And finally, thanks to all of those of you who attended. I hope you enjoyed today's presentation and learned something new that you can apply to your work. After the webinar is over, SPSSI will send attendees a PDF copy of the slides and a link to SPSSI's YouTube channel, where you'll be able to see a recording of today's webinar, which will be posted online later. And as a bonus, do check out those PDF slides. Joshua included some additional slides in the PDF that contain helpful information that you can use as you're trying to apply some of these strategies in your work. So check those out for additional tools and resources. So thank you so much for joining us today, and we hope to see you on one of our future webinars.
Thank you.